students, in our series of lectures, Fourier series part 2, today we will discuss about Fourier series expansion for piecewise continuous function. In part 1, we discuss about the functions which are continuous over the interval of length 2 pi, and we found their Fourier series expansion. But if a function is piecewise continuous over the interval of length 2 pi, what it means? If there are some point of discontinuities in the interval of length 2 pi, then how we will find their Fourier series expansion? For that, we will first discuss Dirichlet conditions. So, what are Dirichlet conditions? Dirichlet conditions for Fourier series expansion. Any function fx can be expanded in form of Fourier series that is a naught by 2 plus summation n is equal to 1 to infinity an cos nx plus bn sin nx if the following conditions are satisfied, and those conditions are known as Dirichlet's condition. First is fx must be periodic, single valued, and finite function. Again, fx must be periodic, single valued, and finite function. Second condition, fx must be continuous over any period because it is periodic function, or important thing, either it is continuous over the period or it may have finite number of discontinuities. This is important because any function is integrable if it is piecewise continuous. Either the function is continuous or it must be piecewise continuous. Piecewise continuous means that there must be some finite number of discontinuities. And if there are infinite number of discontinuities, then we cannot find the Fourier series expansion of that function over that period. So, either it is continuous, or if it is not continuous throughout, then the number of discontinuities must be finite. And third is, it must have maxima or minimum. It must have at most finite number of maxima, minima over any period. So, these are the main conditions that are required to find the Fourier series expansion of a function. So, if the function is continuous throughout the period, Then we discuss how we can find the Fourier series expansion of the function. Again, if the function is not continuous, it has some finite number of discontinuities over the period, that we call it piecewise continuous function. Even then, we can find the Fourier series expansion of the function. So students, you have to keep in mind, I am again telling, either the function is continuous throughout or it is piecewise continuous. In both the situation, we can find the Fourier series expansion of that function. Now, there is also one result, that if the function is continuous at any point, then it is convergent. That is, fx is equal to a0 by 2 plus summation an cos nx plus bn sin nx. So for any x where x, for any x where function fx is continuous, then this series would be, Fourier series would be convergent. It would be convergent to the value what this function fx had. But at the point of discontinuity, what would be the sum of this series? This is important. At the point of discontinuity, suppose for x is equal to a, fx function is discontinuous. Then what will be the sum of this Fourier series? Then this sum is the mean of left hand limit and right hand limit at this point x is equal to a. That is f of a minus 0 plus f of a plus 0. So students, you have to keep in mind, when you will find the Fourier series expansion for piecewise continuous functions, at the point of discontinuity you will be asked to find the sum of the series. So what would be the sum of the series at point of discontinuity? It will be equal to the mean of left hand limit and right hand limit. So now we can find the Fourier series expansion for piecewise continuous function. That is, if a function has finite number of discontinuities, even then we can find the Fourier series expansion, and at the point of discontinuity we can tell the sum of the Fourier series. So students, now find the Fourier series expansion for this function, and we are watching that this function is piecewise continuous. Why piecewise continuous? That over this interval from minus pi to 0, function is continuous. From 0 to pi, it is again continuous, being constant functions. But at x is equal to 0, you can easily find that left hand limit would be minus 1 and right hand limit would be plus 1. So it is discontinuous at x is equal to 0. And such functions are known as piecewise continuous function. That this function is continuous over the interval minus pi to pi in pieces, in 2 pieces, and it has one point of discontinuity. So we already said that Fourier series expansion for that function fx is of the form a0 by 2 plus summation n is equal to 1 to infinity an cos of nx plus bn sin of nx, where a0 can be written using the Euler's formula. A0 would be 1 by pi from minus pi to pi. Why this integral is from minus pi to pi? Because here our interval is given from minus pi to pi. F of x dx a of n is equal to 1 over pi integral from minus pi to pi fx cos nx dx, and b of n is equal to 1 by pi integral from minus pi to pi fx sine of nx dx. So we know that Fourier series of a function is written in this form, and we calculate the values of a naught, an and bn using these Euler formulas. So we will calculate one by one. First we will find a naught, then we will find an and bn. Now here it is a naught would be equal to 1 by pi integral minus pi to 0 f of x dx plus integral 0 to pi fx dx. What I have done, I have used the property of definite integral. I have divided this limit from minus pi to pi as per our pieces given to us, where the function was continuous. That first piece was from minus pi to 0 and second was from 0 to pi. In the same way I have divided my integral, and it would be equal to 1 by pi integral minus pi to 0, and here the value in this case, value of function is minus 1 dx plus from 0 to pi, here value of function is 1 dx, and it would be equal to 1 over pi. Now the integral of minus 1 would be minus x with the limit minus pi to 0 plus again integral would be x with the limit 0 to pi, and this would be equal to 1 by pi. Here upper limit is 0 minus lower limit is plus, we can put the upper limit and lower limit directly, and it would be equal to 1 by pi minus pi plus pi, and that is equal to 0. So I am writing here that a naught will be equal to 0. Now we will find an. An is 1 over pi integral from minus pi to pi fx cos nx dx, and again we will divide our integral in two parts, and that would be 1 over pi integral minus pi to 0 fx cos nx dx. Second would be from 0 to pi fx cos nx dx, and now we will put the limits. During this interval from minus pi to 0, value of function is minus 1, and during the interval 0 to pi, value of function is 1, so it would become minus pi to 0 minus 1 cos of nx dx, and it would become 0 to pi cos of nx dx. Here we will put value of fx is minus 1, and here we will put value of fx is 1. Now we would integrate. Now the integration of cos nx is sine of nx over n, and with the limits minus pi to 0, and in second case it is again integration of cosine x is sine of nx over n with the limits 0 to pi. And students, you know that sine of n pi is equal to 0, sine of 0 is also equal to 0. So you are watching, then when we will put upper limit here, sine 0 will be 0. Second time when we will put lower limit pi here, sine of pi, that will also equal to 0. The same case here, sine of pi is equal to 0 and sine of 0 is equal to 0. So it would become minus sine of 0 over n minus sine of minus n pi over n, and here it would be sine of n pi minus sine of 0 over n, and in both the cases you are watching that all these values are equal to 0. So it is 0 minus 0, here again it is 0 minus 0, so overall an would be equal to 0. That is, so students, I am writing here that an is equal to 0 for all n. We found a naught that was equal to 0. We will find an that is equal to 0 for all n. So now we will find bn. Now we will find bn. Bn is equal to 1 over pi integral from minus pi to pi fx sine of nx dx. Again we will divide our integral in two parts, that is 1 over pi integral, one is from minus pi to 0 with the limits from minus pi to 0 fx sine of nx dx, and second part is from 0 to pi, so integral from 0 to pi fx sine of nx dx. Again, during this interval from minus pi to 0, value of function is minus 1, and during this interval from 0 to pi, value of function is 1. So it would be 1 over pi integral minus pi to 0, and value of function is minus 1, so it would be minus 1 sine of nx dx plus, during this interval from 0 to pi, value of function is 1, so it would become sine of nx dx. Now we would integrate 1 over pi, integration of sine nx is minus cos nx over n, and there is also one minus, and limits are from minus pi to 0. Here again integration of sine nx is minus cos nx over n with the limits 0 to pi. And students, I am writing for you again, reminding you cos of n pi, and that is equal to minus 1 raised to the power n, and it means if n is even, then it would be cos of n pi would be equal to plus 1, and if n is odd, then cos of n pi would be equal to minus 1. And you already know, in case cos 0 is plus 1. So it is equal to 1 over pi minus. Now when we will put upper limit, cos 0 is 1 and this negative is written here, minus. Now we will put cos minus n pi, and you students, I think you know the result. Cos of minus theta is cos of theta, so it will be equal to minus 1 raised to the power n. And why I have put this negative here? Because there was negative, and this plus. Here again, when we will put pi, it will be minus of cos n pi, and cos n pi is minus 1 raised to the power n over n, minus, it would be cos 0 is 1, so this, and now it would be equal to 1 over pi negative, it is minus 1 over n and plus minus 1 raised to the power n, and here it is minus 1 raised to the power n over n, and again plus 1 by n, and it would be equal to 1 over pi 1 over n minus and it would be equal to 1 by pi, and it will be 2 by n minus 1 raised to the power n over n. So students, just look at here. We know cos n pi is minus 1 raised to the power n and cos 0 is 1, and I have just put the lower and upper limits in both the cases, and just find this. So look at it here, that Bn is equal to 1 over pi 2 by n minus 1 raised to the power n over n. Now we will further simplify it. I am erasing from here. It would be equal to 1 by pi 2 by n minus 1 raised to the power n over n. Now students, it would be equal to, I am taking n is even, that when n is equal to 2, 4, 6, 8, when n is even, it would be 1 by pi 2 by n minus, it would become positive, that minus 1 raised to the power n even number, it would become plus 1, so it would be equal to 1 by n, and we will left with 1 over n pi in case when n is equal to even. Now again, when n is odd, it would be equal to, now if n is odd, then minus 1 raised to the power any odd number, it will be equal to minus 1. So we will have, it is plus. And in that case, it would be equal to 3 by n pi if n is odd. Why I have written Bn in this form? Because we have to find the value of B1, B2, B3, B4. So now we can easily write that what will be B1? B1, here 1, n is your odd, so it would be equal to 3 by pi. B2, here n is even, so from here it would be equal to 1 over 2 pi. Again B3, Again n is odd, so it would be 3 over 3 pi. Again b4, here n is even, it will be equal to 1 over 4 pi, and so on. So in this way we will find b1, b2, b3 and b4. So students, for this function fx, which was piecewise continuous function, we find a naught, and that is equal to 0. We found an, that is again equal to 0, and we have found bn in this way, where b1, b2, b3, b4. So we can write the Fourier series expansion by after putting the value of a naught, an and bn, and it would be equal to, for your convenience I am writing here that it would be equal to, when we will put a naught is equal to 0, it will become 0. Again, when we will put an is equal to 0 for all n, this term would become 0. We will left with only one term, that is summation n is equal to 1 to infinity bn sin nx, and if we put n is equal to 1, 2, 3, 4, 5, it will be b1 sin x, b2 sin 2x, b3 sin 3x, b4 sin 4x, and so on. And we have already found the value of b1, b2, b3 and b4. If we will put here, it will be 3 by pi sin x plus 1 by 2 pi sin 2x. It will become 3 by 3 pi sin 3x. Again it is 1 by 4 pi sin 4x, and so on. So this is the Fourier series expansion of this function f of x. So students, for this piecewise continuous function, we have found all a naught, an, bn, and substitute the value of a naught, an and bn in the expansion, and finally this is the Fourier series expansion of this function. Now if we are asked to find the sum of the series at x is equal to 0, that what will be the sum of the series at x is equal to 0? Students, we know that function is piecewise continuous over these two intervals, and it is discontinuous at x is equal to 0. So at all the points except 0 in this interval from minus pi to pi, function is continuous. So this series will continue. This series will converge to fx at that point. But in the start we discussed that at the point of discontinuity, what will be the sum of this series? And I already told you that this sum will be equal to the average of left hand limit. Now the point of discontinuity is 0, so left hand limit will be written in this form, and right hand limit at 0 would be of this form. And students, you know, here the left hand limit would be minus 1, and here right hand limit from here would be plus 1, and that sum will be equal to 0. So the series of this, the sum of the series at x is equal to 0 would be equal to 0. So in this way we can find the Fourier series expansion of piecewise continuous functions over the interval of length 2 pi and we can find the sum of the series at the point of discontinuities. I hope now you can find the Fourier series expansion of both continuous and piecewise continuous functions over the interval of length 2 pi, and also you can find the sum of the series at the point of discontinuity. Okay students, practice some more questions from your textbook. Thank you.